Hello, here we will use the algorithm for inverting matrices to compute the inverse of a linear transformation. It was actually the motivating construction for matrix multiplication in the first place, that matrices are nothing but records of linear transformation. So if we have two vector spaces, coordinate vector spaces of dimension n, it's the same because we want to invert our transformation, and the corresponding matrix will have to be square. Then the inverse transformation we can make sense of even without assuming that it is linear and it is given by a matrix. It's just a general concept which is applicable to arbitrary maps. The conditions are, again, two equations that starting at this end, going along the inverse process and coming back with the f, so computing this composite is going to be the identity doing nothing at this end. So going this loop is the same as doing nothing. And in the opposite order, starting with f and undoing it, well, should be undoing it, should be giving us again doing nothing composite at this end. So that is the pictorial way of representing the two equations. Two equations would just say that f inverse is the inverse transformation to f. As matrices, inverses, when they do exist, they are unique. It's the same arithmetic proving it. But now we can, for linear transformations in this situation, we could really compute the inverse transformation by computing the inverse matrix and then writing a transformation with this matrix. So that will be done in this example. The transformation will be on the vector space of coordinate three vectors. The explicit form on arbitrary three vector is as follows. To make it linear, we have to write linear functions in each of the coordinates of the answers. Let's imagine something like that. For the first coordinate of the answer, the second will be, say, this. And the last will be this. Transformation corresponds to the 3 by 3 matrix with entries and we need to find its inverse. So okay, let's do it the same way as we did before, doing Gauss algorithm on an extended matrix, extending this by the identity matrix. We already have a perfect pivot in the perfect position. We just need to start eliminating in the first column. Two transformations will do it for us. Row 2 minus 3 copies of row 1. Row 3 minus 2 copies of row 1. And we'll have 0, and then we'll have 1 without 3 copies of 2, 1 without 6, negative 5, and 2 without 9 is going to be negative 7. Here we'll have negative 3, 1, and 0. Creating 0 here, we will have to compute the difference of 3 and twice 2, so that will be just negative 1. And then 1 without twice 3, 1 without 6 will be negative 5. We'll have -2, 0, 1 in the extended part. That is good to be the second pivot. We need to scale, we need to change the sign and put it in the right place. So let's do these transformations one by one. Negative row 3 just to change the sign. I can change the sign of the second row at the same run of the algorithm. So negative row 2 will be done as well. We'll have 5, 7, 3, -1, 0. Then we have 0, 1, 5, 2, 0, -1. And then the swap. Okay, now we have our second pivot in the place where it should be, and we can eliminate below. That will be done by this transformation, row 3 without 5 copies of row 2. So we'll make 0 here, but then in this position, 7 will be changed into 7 without 5 times 5. 7 without 25 is -18. 2 without 10 will make it -7. -1 stays. And then 0 without -5 is going to be +5. We are almost halfway through. If we scale it down to 1 by dividing the row 3 by -18, we will create a row echelon form. With ones on the diagonal and zeros everywhere below. In the process, the last row in the extended matrix will have to change by just changing the sign of all its entries and adding the denominator 18. 7/18, 1/18, -5/18 is what it is now. Now we're ready to reduce this row echelon form to the identity matrix in the first half. The first reduction run will be just getting rid of 5 and 3 using row subtractions. Row 1 minus 3, row 3, and in parallel row 2 minus 5, row 3 are the transformations we need to do. That will make the last column looking perfect. The last row in the extended part is what we're transforming with, but itself it's not transforming. So I'm just copying it and now subtracting from row 2, row 3 5 times. 2 without 35/18. So 2/18 is 36/18, and then without 35/18, it will just leave me with 1/18. 0 without 5/18 will be -5/18, and then -1 together with 25/18. So it will be as if I'm subtracting from 25/18. It will be the same as 7. And in the first row, again, there will be some interesting changes. So I'm subtracting 3 copies of the last row out of the first. 1 without 21 over 18. It will be, with common denominator, it will be 18 without 21 all over 18. So that will be negative 3 over 18. In this position, 0 minus 3 over 18, it will be negative 3 over 18 again. And in this position, 0 without negative 15 over 18, so it will be just 15 over 18, positive 15 over 18. Finally, the last move to get to the answer, I need to get rid of this 2 above my second pivot. Row subtraction again. At this step, the left-hand side is in this perfect shape, so the right part of the extended matrix will be the answer. The answer is already visible. The second 2 rows of it are already visible in here because they're not changed. The only transformation happens in the first row. Subtracting the second twice from the first. Negative 3 over 18 without 2 over 18 will be negative 5 over 18 in here. Negative 3 over 18 without negative 10. So it is positive 10 without 3. 7 over 18. And 15 minus twice this. So 15 minus 14 over 18. All over 18, it will be just 1 over 18. And then looking at the answer, it makes sense to take 1 over 18 in front as a common multiple. The rest will be negative 5 on the diagonal, 7 in these places, and in the remaining places 1. So that will be just the matrix of numerators of this matrix entries, and it is it is sort of repeating the pattern, because in the original matrix again we have the same sort of shapes occupied by the same numbers, but the final answer is not the matrix. The final answer is the transformation of a generic 3 vector with this matrix. So I'll just write the coordinate vector which is the result of this transformation, and that is the vector of which is a product of this matrix and x, y, z. So these are the coefficients of x, y, and z of the coordinates of the input in the answer. That is the first coordinate of the answer. The second, and the last. So our job is done here. We computed the inverse transformation. Of course, it is laborious to check that the composites of the transformation and its inverse in 2 possible ways are the identity. It's easier to check that the product of the 2 matrices is the identity by just multiplying them together and seeing that the result is identity. But that I will not do here. That can be delegated to you as an exercise.